Hi friend, welcome all to my educational channel Math A to Z. Today we discuss all about the set Zn. And what is Zn? This set is called integer modulo n. Okay, and this same set contains n elements which are 0 plus 1 plus 2 plus 2 n minus 1 plus. That is, if we divide any integer like p by n, then we can get remainder 0, 1, 2 to n minus 1, and all the element like p which gives remainder 0, remainder 1, remainder 2, remainder n minus 1. When we divide p by n, then these elements is 0 plus, in 0 plus, these elements in 1 class, and if gives remainder 2, then all those elements is in 2 plus. Okay. For example, if we divide or if we take Z5, then this set also contains 0 plus, 1 plus, 2 plus, 3 plus and 4 plus. And if we wish to write 0 plus, then 0 plus is 0 plus minus 5 plus minus 10 to infinity. Because if we divide 10 by 5, then remainder is 0 and all the elements gives remainder 0. Similarly, 1 plus is 0 plus 1 plus minus 5 plus 1 plus minus 10 plus 1 and so on. Here we see that from here one element is 11 and one element is minus 9. Now if we divide 11 by 5, then obviously remainder is 1. Also if we divide minus 9 by 5, then obviously remainder is 1. So 11 and minus 9 both belongs to 1 class. Clear? So our concept of Z5 or Zn is clear. And here all the elements is a class, and we know that these are all the equivalent classes. These are 0 plus, these are 1 plus, these are 2 plus, and these are n minus 1 class. Now, if we take a particular example as Z3, then we get 0 plus, 1 plus, 2 plus, and we make a composition table with respect to plus 3, that is addition modulo 3. Then we get this is 0 plus, this is 1 plus, this is 2 plus, this is also 1 plus, this is 2 plus, and this is 2 plus, this is 0 plus, this is 0 plus, this is 1 plus. Okay, here we say that from the multiplication table or the composition table, the set is closed under plus 3. And obviously we know already that integer modulo, set of integer modulo is associative. So this is associative property in the set. Now from this row, first row and first column, we say that for all A class belongs to Z3, A class plus 0 class equal to A class, or 0 class plus A class equal to also A class. For A class equal to 0 class, 1 class, 2 class also. So we say that 0 class be the identity of this set with respect to class 3, and in each row and each column we see that here is also 1 class, here is here is first row, here is 0 class, here also 0 class, and here also 0 class, and 0 class with identity. So we can write here, from here 2 class plus 1 class equal to 0 class, and 1 class plus 2 class is equal to 0 class. So we should say that 2 class is the inverse of 1 class. Similarly, 1 class is the inverse of 2 class. So 1 and 2, 1 class and 2 class are inverse to each other. And also this relation shows that 0 class plus 0 class equal to 0 class. So the inverse of 0 class is 0 class itself. So all the element of this set give inverse. So all the 4 property of group is satisfied by Z3. So we say that this is a group with respect to class 3. Also here an important point, this is the principal diagonal, and with respect to the principal diagonal the composition table, this is 1 2, this is 1 2, this is 0, this is 0. So the composition table is symmetric. So the group is also commutative. Now we have to comment here that the Z3 with respect to addition modulo 3, Z3 with respect to class 3 is a commutative group or abelian group. Abelian group. Now we consider this group with respect to dot 3, that is multiplication modulo 3. Then we make a composition table as 0 plus 1 plus 2 plus 0 plus 1 plus 2 plus. Here we multiply this plus and then divide by 3, and this gives 0 plus 0 plus 0 plus 0 plus 0 plus. This is 1 plus, this is 2 plus, this is 2 plus, this is 2 to 4, that is 1 plus. Clearly from the first row and first column we say that this set, that is Z3, is not a group with respect to dot 3, that is multiplication modulo 3. Now if we delete 0 plus from this set, that is if we take Z3 minus 0, so we get this row and this column, delete here, and this set must be a group because it hold closure property, it hold associative property, and it hold identity because 1 is the identity from first row and first column, and also 1 is the inverse of 1 and 2 is the inverse of 2, and this is also abelian group because it is symmetric. Now we consider Z4 minus 0 plus. This is 1 plus 2 plus 3 plus this 3 element. Now we make a composition table with respect to dot 4. 1 plus 2 plus 3 plus 1 plus 2 plus 3 plus. Here this is 1 plus, this is 2 plus, this is 3, this is, and this is 2 into 2, 4 plus, that is 0 plus. 2 into 3, 6 plus, that is 2 plus. 3 into 2, 6 plus, that is 2 plus, and this is 3 into 3, 9 plus, that is 1 plus. And from this element, we say that this set is not closed under dot 4. So this is not a group. Okay. Also, here we also see that 2 plus have no inverse, because in the row of 2 plus or in the column of 2 plus there does not appear 1 plus. Okay, so 2 plus have no inverse, but 3 plus have inverse. 3 plus into 3 plus equal to 1 plus. This is the identity. So 3 plus have inverse. So it is important to note that any element in this set which is less than 4 and prime to 4, all less than 4, 1 plus 2 plus 3 plus are all less than 4, but which is specially prime to 4, then that is 3 plus and 1 plus have the inverse. But if 2 plus is not prime to 4, so it is not inverse exist. Now we go to the point that in Zn all the element which is not prime to n, then the inverse of this element does not exist. But if in Zn all the element which is prime to L, then the inverse must be exist. And this is the if and only theorem or only property. Now we discuss this property. The property is, if U plus belongs to Zn and GCD of UN equal to 1, that is prime to each other, then U plus have inverse. And any element in a group which have inverse is called unit element, that is U plus is unit. Also, if U plus is unit, then we must have GCD of U comma n equal to 1, that is prime to each other. So this is the important, this is if and only property. Okay, if we take GCD of UN equal to 1, then U plus is unit, and if we take U plus is unit, that is invertible, then GCD of UN equal to 1. Now we first prove by taking this, we prove this. Here GCD of UN equal to 1. So from the theory of number system, we know that there exist two integers a and b belongs to Z such that AU plus BN equal to 1. Okay, and this relation can be written as AU minus 1 equal to n into minus b, and this relation shows that AU minus 1 congruents to 0 mod n, because this is multiple of n, so this is congruent to 0 mod n. Now AU whole class this is equal to, this is congruent to 1 plus mod n. Now this relation A class into U class, this is equal to 1 plus mod n. If A class belongs to Zn, then from this relation we say that A class is the inverse of U class, and if A class does not belong to Zn, then we have A class equal to R class mod n, where R class is in the range this. Okay, because if we divide A by n, then the remainder R must be 0 less equal to R less than n. Now from this relation we get A class into U class congruent to, this is also congruent, R class into U class mod n. And from this relation and from this relation we say that R class into U class congruent to 1 plus mod n. So from this relation we say that R class belongs to Zn and R class is the inverse of U class. So U class is invertible in Zn if and only if GCD of U and n equal to 1, that is U is prime to n. Now we prove the second part. From this we get this part. Here we take U class is the unit in Zn. Since U class is unit, so there exists P class belongs to Zn such that U class into P class congruent to 1 plus mod n. Okay, now U class into P class congruent to 1 mod n, this relation gives UP minus 1 is equal to S into n. This class is equal to 1 class. This means when we divide UP by n gives remainder 1, and if we subtract the remainder 1, then it is completely divisible by n, and here the quotient is S. So we can write this. Now from this we get UP minus Sn is equal to 1, that is U into P plus n into minus S is equal to 1. Here P and S both are integer. So also by the theory of number system we see that GCD of P and n, this is equal to 1. So we can prove this result. Now in summarizing the result we say that in Zn the element which is less than n and prime to n, these are only the unit element, or these are only the element which is invertible or inverse exist. Now we consider a set, name this set as Un, and this is the set of units modulo n, because here consist only these elements which is units of Zn. Okay, and Un must be a subset of Zn. Now we consider the set Un, which consist those elements of Zn which are units in Zn, and this set can be written as Un such that U bar belongs to Zn and GCD of UN equal to 1. Now we have to show finally UN, that is the set of unit modulo n, is forms a group. Here we take two elements, U bar and V bar of UN. So U and V are both prime to n. So we say that U into V must be prime to n. That is U bar into V bar. U bar into V bar must be belongs to UN. So this is the closure property and this is the first property of group closed. We know that the product of multiplication modulo n is associative in Zn, and since it is held in mother set Zn, so by hereditary property we say that this is held in UN. So the second property, that is associative, is also held. Associative is also held. Now for the third property, that is the identity property, we know that one class belongs to UN because one class is the unit and inverse of one class is one class itself, and one class have the property such that one class into U class is equal to U class into one class. This is equal to U class for all U class belongs to UN. So we say that one class be the identity, and this is the third property of the group. Also it is clear that we first take those elements of Zn which have inverse. So for all U bar belongs to UN, there must exist V bar belongs to UN, such that U bar into V bar is equal to 1 bar. Okay, because U is prime to n, so its inverse must be exist. We prove here. In addition, so inverse property fulfilled, so the group is whole. All the properties of group is whole. So UN respect to dot n, multiplication modulo is a group. Together with this, if we consider the abelian property, that is commutative property, this is also whole, because we know that in the multiplication modulo n in Zn, A class into B class, this is equal to B class into A class. So this is a commutative group with respect to multiplication modulo n. Now we have to find the number of element of UN. We know from the number system or Euler phi function, the number of numbers of integer less than n and prime to n is phi of n. Okay, so here UN in this group, the number of element consists is phi of n, and this is the order of the group, because the order of the group is defined as the number of element of the group. Okay, so order of UN is equal to phi of n, and this is the order of the group, and this is very, very important group of group theory, and this is the today's discussion. Thank you very much.